Right. There he is.
Okay.
Ah, here he is.
Okay.
Yep.
Let's see. Andrew, what happened at the end of the last class?
I don't really know.
Well,
So,
I know what happened at my end. My Windows 10 just froze. I had to power the machine down.
Ooh.
Yes.
so for us, we were just left with a picture of your desktop, and it took us a while to figure out that you just weren't there anymore, and we just slowly shuffled out. We were very confused. It sounded almost like you had gotten up and had to walk away because someone like needed you right away for some reason. So we're just like, okay, we'll just sit around till he comes back. And then we looked at your clock, and it
wasn't
started
moving, huh?
to disagree. It started disagreeing with ours. We're like, oh.
That's how I noticed there's something wrong too. Yeah, I was talking and I thought this computer screen seems oddly still. And then it took me a little while to realize that my machine, there was no mouse, it was just completely locked up. But the screen, it just had a normal looking screen, but I ended up, no control, delete, nothing would do anything. I had to hard boot, I had to pull the plug on the computer and shut it down. That's never happened before. It's the first time I've seen Windows 10 do that.
I've seen plenty of editions of Windows doing nonsense like that where it won't even respond to like you hitting the on-off button sometimes.
Yeah, but usually
But not Windows 10.
Yeah, right. It's the first time I've seen it in Windows 10. I've seen it in lots of other versions of Windows, but yeah, I'm lucky. We're lucky it happened at the very end of the class. So.
Right? Yeah, I guess the OS corrupts so badly that it can't even handle like a air trap to blue screen.
Yeah, that's pretty bad. Usually you can at least Control-Alt-Delete and reboot the computer, but it was completely frozen. Anyway, so I was wondering so you just saw a frozen screen just like I saw.
Yeah.
Okay. Huh. I thought maybe you would see one of these like science fiction kind of fade outs where, static or something like that.
Nah.
Okay. So, let's see. Okay, you can see the desktop, right?
Yep.
Yeah.
Okay. What I was going to want to do is just show you more things about writing performance code, about writing, what happens when you try to write code that tries to be fast. Okay. So I've been writing more versions of these searches. Oops, wrong folder. Okay. Okay. So let me summarize what I've been trying to do. You want to see, like, modern parallel programming is about trying to process, mostly it's these days it's big data. So this has been a nice example of something that approaches what you do with big data. So there's 1,000 files in here for a total of a couple gigabytes of data. And I've also joined all the files into one big file. So I can either work on one big file, which is 2.3 gigabytes, or work on 1,000 small files. Both are good ideas because sometimes you're given a huge data file, sometimes you're given lots of little data files. You don't quite process them the same way. But in our case, by having this guy be the concatenation of all these, we get the same results. So we're comparing apples to apples. So we have the same data in here that's in all these files here. And then we can just look at different kinds of results. Okay. Now, if you really want to understand what's going on when you write this kind of code, you have to build up from simple cases. Okay, so I started out by just doing something as simple as counting the bytes in the file. Okay, That's the simplest thing you could do, is just count the bytes in the files. Okay, so over here I have the files that mostly work on just this data, and on this folder I have the programs that work on all the subfolders. I kind of just, because I've written so many versions, I put them in 2 different folders to keep track of them. Okay, so the simplest thing is just count bytes. Okay, this counts the bytes in the huge file. This counts the bytes in all these files. Then I went from counting bytes to counting lines. You know, that's just a little bit more work than counting bytes, and it should take a little bit longer. But by doing, these are simple programs. By doing simple programs, you can you can understand the code better, and you can get a better feel for how they compare. Then went from counting lines to searching. You know, and first search sequentially, and then try to parallelize the searches. Okay, so it's a real progression of ideas, and it's the progression that gives you a sense of when you're doing something right and when you're doing something wrong. If you just kind of, what textbooks and a lot of people just do is go straight to writing parallel code. They get all the cores running, and they assume that they're doing something right because all the cores are running. And as I pointed out here, you can get all the cores running, and you have a program that's 10 times slower than just a single-threaded program. Yeah, it isn't good enough to just write a parallel code and see it use all your cores. You got to build up slowly, and make sure that you're actually improving things. You know, you don't want things to get worse. You want things to get better. Okay, and the only way you know things are getting better is to start from something simple and make it more complex, and hopefully it gets faster as you make it more complex. Okay, and that's not always worked. In some of these cases, some of the attempts to parallelize actually turn out slower, and some of the attempts at parallelizing turn out faster. And it's only by comparing them that I know which ones are working and which ones aren't working. Without something to compare it to, you just don't know if you're getting better or worse. Okay, so now in terms of parallel, like for example, when you read the files, just count bytes. What that brought up was, what's just the fastest way to open a file and read it? If you don't know a fast way to read a file, you can't process the data in parallel any quicker. So you know, I found out that some ways of opening in files are not good, and some ways are better. Okay, so in these files, I've stayed away from what turned out to be the bad ways to read a file. So I'm mostly here working with good ways to read a file, but then there's different ways to parallelize things. Pardon me?
That was your echo.
Yeah.
That was an echo.
Okay. All right. So let's see. Try to show what would be a good thing to look at. Since we met on Monday, I've been working on these memory mapped ones, and they're interesting to write. They're actually they're not too hard to write, but something's kind of wrong, I think, with the Java way of doing, or I'm probably using the memory map files a little bit wrong. When I counted bytes and counted lines, memory map did a big improvement. Let me show you real quick. This counts the bytes. See, it took 700 milliseconds to count. Yeah, and that's not parallel or anything. That's just doing good, solid, fast I/O. Okay, then you memory map it. And it's even faster. Okay, it's twice as fast almost when you memory map it. Okay, so in terms of just reading through the data, I have a baseline that I can read into memory 2.3 gigabytes of data in 300 milliseconds. Okay, that gives me a baseline, in Java at least. Okay, then if I count lines, here's counting lines without memory mapping, just okay, notice it slows down quite a bit because to count lines, I have to look at every single byte in the file. And what you do is you're looking for new line. You're counting the new line characters. when we read bytes, we actually don't even look at the bytes in the file. We just count the number of bytes. Essentially, we count buffers full. The program for counting bytes really just reads the file in one buffer at a time and just says, oh, that buffer was this big. So I just count. Now, every single buffer is read into memory. There's no cheating going on. We're not just opening the file system and asking, if the fastest way to find how big a file is just ask the file system. It'll tell you it's 2.3 gigabytes. If you just right click on this, the file system knows how many bytes are in a file. So we're not asking the file system how many bytes are in the file. In this code, we're actually we're having the file system open the file, read every sector of the file into memory, and then just counting out how many sectors there were, essentially. Okay, so we're not looking at the data. Whereas in counting count lines, there's no question you have to at least look at every single byte. Okay. Now, let's see. Now, memory map that. It's a lot faster. The memory mapped access to the file for counting lines is significantly faster than just doing it without memory mapping. This is using the file system, the stream system of the Java library. This is memory mapping the file, which essentially makes the file an array in your virtual memory space. We talked about that the other day. This makes the file essentially one big array in your memory space, and then it's up to the virtual memory system to page the data in for you. Now, the virtual memory system still gets the data from the hard drive, just like this one does. But the virtual memory system's one of the most tuned parts of the operating system. So by relying on the virtual memory system to bring the data into memory, it ends up being a lot faster. The virtual memory system is just very well designed.
I have a question. Is that about as fast as you could possibly do that operation there?
I have no idea. My guess is no. The way to know that, my guess is it's probably not even close to the fastest it can be done.
Really?
Yeah. First of all, we're using Java, not C, and there's lots of tricks you can use on this stuff. So I don't think this is as fast as it could be. I'll show you some benchmarks in a minute that give me a sense that this is not as fast as it could be.
That's about 1 billion characters a second.
Well, okay.
That would be on your machine, what, like 4 instructions per character?
I don't know, but I put grep on this machine.
Mm-hmm.
Okay. Now this is a Windows version of grep.
Mm-hmm.
Okay. So grep version 2.5.1. Well, actually, okay. I have 2 versions of grep. I'll show you why. Okay. And I want to count the number of aardvarks. Did I spell that right? Aardvark in the data file. Oh, now I want to time that. There's 21 aardvarks in there. Less than 2 seconds.
Nice.
Okay. Right. So now, and if you watch, that didn't seem to be multi-core. That probably was this is an old version of grep. This program's from like 10 or 15 years ago. It's an old version of grep, and whoever wrote it knew what they were doing. Okay. Now, I got another version of grep on here. Okay, there's another version of grep. Same thing. It's not as fast. It's about twice as slow. These were compiled by different people. I don't think they're different versions of grep, but I do think they were probably compiled differently. So one issue in this thing is, how did you compile your code?
Oh, no.
Okay. Now, I found out to my amazement yesterday I have Windows subsystem for Linux on this machine. Okay, so I thought, okay, let me try this in Bash. And then I find out that Microsoft's just amazing. When you install Windows subsystem for Linux on a machine, it only installs it for whatever account you happen to be logged in on. So I don't have Windows subsystem for Linux on this account. I have a couple accounts on this machine. So I can't show you this in Bash, but in Windows subsystem for Linux, the version of grep that comes with Windows is blazingly fast. It greps this file in, I think, a little under a second. Or, yeah, it greps it about a little bit faster than this guy did. Okay, so grep is a good benchmark for what we can expect to get. So grep can search this file really fast. You know, grep's going to be written in C. It's single core. It's not a multi-threaded program, so it's using one core in the file system as optimally as possible. I don't think it's doing memory mapping, because if you run this, yeah, I'm running the Windows version. Yeah, if you run this and you watch the memory, you don't see any blip in the virtual memory system. So it doesn't look like it's memory mapping the 2 GB file. Okay, and it also, you see a big spike. Yeah, it's kind of hard to tell. I don't think it's multi-threaded, but
It almost looks like it is.
I know, but that may just be the operating system moving the process around from core to core. See there,
Yeah,
it didn't move at all. See that spike? It was all in one place. That spike seemed to have been in one place. So it's an old version of grep. This grep is pretty darn old. Where is it? 2000.
Oh,
It's
so
20
it's
years.
20-year-old version of grep. No,
Yeah.
it was not multi-threaded.
No, it's not multi-threaded. Yeah, it's just an old version of grep that I happen to have had on my machine. I don't remember when I downloaded it. Okay, yeah, and the current version of grep is, I think, 2.6 maybe. Yeah, so grep is, but the most recent version of grep would be part of Windows subsystem for Linux. Unfortunately, I can't show you that one because I found out that this account doesn't have Windows subsystem for Linux on it, because Windows subsystem Linux only installed itself on one account.
I can demonstrate that if you want.
You have that file on your machine?
I don't have that file specifically. I just have another like 2 GB file that I can use. So exit full screen, toss that onto another monitor. So open up a new window. Where are you? All the data.
Programs like grep are really good benchmarks for doing this kind of stuff. Like, actually, I tried awk, grep, and sed. Those are 3 different programs that are part of Linux that will do searches in large files for you. And grep and sed were fast, awk wasn't. Awk was not particularly fast. But grep and sed, sed stands for stream editor. It's an old Linux editor. The ED stands for editor, and S stands for stream. Okay, so it's just another program that'll search files for you. Grep is the most famous of them. So, did you get yours working?
I'm just verifying that this folder has it, and to open the folder takes a while because it's the whole thing. Okay, well, so give me a minute.
Okay, now, so, but see, when you want to find out what's going on in the world, you have to have some standard. You have to have some benchmark that you can compare to. And things like grep, things like basic tools in Unix are good ideas. That, use them as your benchmark. So we know that a program can grep this file really fast. uh,
Yeah.
see there it's telling me which line number has each instance of aardvark. Okay, so that took this is the slightly slower one. That took 4.5 seconds. Now notice that we are in the ballpark of this version of grep. This grep took 4.5 seconds to not only find all the aardvarks, but tell us what line number they're on. Okay, in our program, oh, that was only, I'm sorry, that was only the one that was counting data. So like I can run one of the programs that searches. Okay, there was one of my parallel versions, the same speed as this one. Okay, okay. I've
All right,
not.
I got
Yeah.
a version of it.
Okay, of grep.
Yeah. I don't know how you would let me present.
Oh, I don't know. I think you just try clicking on screen share.
Professor
Request
Kraft, if you
control.
stop sharing your screen, then anyone else can share theirs.
Oh, I have to stop sharing mine?
Yep.
Okay.
Now you can do
All
it.
right. Video. Edit. How do I share my screen?
Do you share screen? The green share thing?
Oh, duh. It's literally
Yeah.
right there. Host has disabled screen sharing.
Yeah,
Oh,
and
probably that's the security. We had to worry about Zoom bombing. So we were told to disable screen sharing on all these classes. I don't even, yeah. I'm not sure where I go to reinstate it. Yeah, that's part of the security settings. Okay. Well, you run it and just say how fast it was.
All right. So you had grep C.
Well, grep minus C counts the occurrences.
Mhm.
Grep minus C will count occurrences for you. And then if you want to actually do the search, you do grep minus NO. Well,
Aardvark. Takes about 4 seconds for me.
on Unix Windows substitute for Linux?
No, on just a straight Linux machine.
Oh, okay. Yeah, but see, now we're comparing apples with oranges because your machine could be very different than my machine. So we're not getting a relative comparison here. That's
Oh yeah, and I've got grep version 3.3, which is 18 years newer than yours.
yeah, but the key is not really how new grep is. The key is really more, well, was it written multi-threaded or not? I'll bet it isn't. I'll bet anything
It
not
did not appear to run multi-thread because
Yeah.
I have a system monitor. No, it's not.
Yeah.
It's just pinning one core.
Core. Very few people have gone back and rewritten their code in multi-threaded ways. The world is full of tons of very well-written code. Very few people are going back and ripping it all out and rewriting it. So tools like grep, which have been around for a long time, they're already pretty fast even on one core. You can see that this is blazingly fast on one core, as fast as my program is when I try to parallelize it. Okay, but that's what you want to do, is you want to find benchmarks. You want to find something reliable that you can use as a basis for knowing whether you're making progress or not, or whether you're in the right ballpark. You don't want to be in the wrong ballpark when you're doing this stuff. Okay, all right. So now I was showing you that the memory mapping seemed to give me a real performance boost when I just did it counting bytes and counting lines. But when I go to searching, I don't get I lose the performance of memory mapping. This is what is kind of puzzling me. So let me show you a couple examples. here's the fastest sequential search I have. Okay, it uses a file input stream, but it does its own buffering. It's doing its own buffering of a file input stream, and that seems to be as fast as I can do the I/O to do a file input stream with my own buffering, and then it just searches each buffer for aardvark. It's pretty straightforward, not too many lines of code. Okay. Oops. This okay, not quite 7 seconds. Not quite as fast as that grep version. Okay, it's Java. Oh, another thing that's really I started wondering, if you're really going to do performance things and you're trying to measure, I'm actually probably not giving Java the right. Okay, Java's got a just-in-time compiler, right? The just-in-time compiler in the Java virtual machine needs a while to compile things. These programs are running for such short periods of time, they may not actually be getting the full benefit of the just-in-time compiler.
Well, my question is then, does the JIT operate on numbers of loops done in a particular section of code?
Who knows?
Or does it go by like a number of seconds?
I have no idea. I just know that they tell you all the time that the JIT compiler doesn't kick in fully until the programs run for a little while. Now, if you're running a server that runs for hours, who cares? But
right.
what I need to do here is probably maybe like make the file size way larger so that the program runs for more than a few seconds. Because
you could just try to chuck all 30 gigabytes into a file.
Right. I haven't done that yet, and that's one of the things to try to do. Because I don't know for sure. I may not be getting the full benefit of the. This is like with C and C++, it's compiled code. With Java, the compiler is giving you byte code. Then the just-in-time compiler in the Java virtual machine is giving you real code, but that takes a while. And you're always warned that Java programs can take anywhere from a few seconds up to get everything compiled in the JIT compiler. So I don't know. So these programs may actually be doing better than I think. They just haven't been JITted well enough. Okay. Now let me do this one with the memory mapping. Okay, so now here's the memory mapped sequential search. The only difference is that instead of opening the file and reading in buffers, this thing steps through the file. Let's see. Well, it memory maps the whole file as one big. Essentially, you'll see it in the task manager. It basically bumps my virtual memory space by 2.3 gigabytes. So it puts the entire file in my virtual memory space. Then I start stepping through the file as if it was a big array. And as I do that, the file will page into memory. And this is how the other memory map programs work. And they get very good performance boosts out of that. And this one ends up running exactly the same. Hardly any difference. On average, it runs at exactly the same speed as the file version. The memory map version gets no speed up over the file version. It did when I was counting lines, but it doesn't now. And I'm very suspicious it has something to do with, I'm not doing real array axes. I'm having to, I have to step through the memory map file using this get method. And I'm kind of suspicious of that get method. Maybe the JIT compile, this is where I'm throwing it, if maybe it's not getting JITted well enough, maybe it's not being optimized well enough.
It's actually doing a bunch of function calls.
Yeah, and who wants to step through an array doing one function call per array axis? That seems nuts. I'm doing 2 billion array axes. So this, to me, looks like a real failing in the design of the memory map file system. And I bet it's just that there's some trick I don't know about.
You're supposed to be able to get like an actual array out of this.
Well, we talked about that the other day. You can't. The Java does not give you the array. Now maybe I'm supposed to carve out pieces of an array from.
Hold on. Why don't you try first giving the JVM more memory? Because it might be saying at runtime, can I load this directly into memory? How much do I have access to?
No, no, no,
I
no, no.
don't have 2 gigabytes. All right, we'll do this piecemeal then.
No, no, okay. No, no, no. That's not how memory map files work. That's not the idea. Okay. This is, first of all, the memory, when you memory map a file, you completely bypass the heap. This has got nothing to do with the heap. The memory map file, the Java virtual machine asks the Windows operating system to directly map this file to virtual memory. Now, if I run this program, you see it.
Oh.
See, it's page faulting 2 gigabytes in, and then when it was done, all that memory was decommissioned. Use that ramp there is page faulting in step by step 2.4 gigabytes of memory. It's not done through the file. It's not done through the heap. It's done by the operating system. This is a feature that was added to the Java virtual machine and just not too long ago. It's actually very clever. You know, it forces the Java virtual machine to talk directly to the operating system to ask it to do the memory mapping. But that ramp up is page faults. That would be nothing but page faults as the file gets, as I loop through the file in this loop, you know, the file has been allocated as one big array. And then as I loop through that array from beginning to end, it's going to get page faulted in by the file system. Okay. And I mean, it's no slower than, it's just as fast as if I read it as a file, but it should be faster. Yeah. And I think what the price I'm paying, I think is all the, I'm doing 2 billion calls to get. And I'm afraid that I'm being hammered by the function calls. So
you could try to do the bulk get methods.
But then I can't look at the individual bytes.
Well, I have a question.
Uh-huh.
Are you doing 2 billion function calls times 8 times?
Yeah, actually, right, exactly. Yeah, because I have to, I check 8 bytes, then move over 1 step, check 8 bytes again. Yeah, so yeah, I'm doing a lot of function calls. I bet anything, if I wrote this in C++ and memory mapped it, this would be blazingly fast. Because if I did this in C++, I would be doing array access. Because C++ gives you the memory map file as an array data type. You know, it is an array. For some reason, Java is not giving it to us as an array. It's giving it to us as an array inside of an object, and we have to call these get methods.
And it won't let you get the actual array because
No,
it says it doesn't have it.
It's there. It's gone from us now, but it's certainly there. You know, you can watch it. There it is. It's appearing in memory. But why Java won't let us directly access it, I don't know why. I'm not sure. Maybe there's a trick that I've been trying to read about this, trying to find it, and I just have not been able to find a good answer to this question. It's possible that one answer is, why are you stepping through memory byte by byte by byte? You know, usually that's not how you access data, byte by byte by byte. But at the same time, you know, you should, I mean, C++ would let me do this. I mean, if this was C++, I would not be paying any performance penalty for using a memory map file, okay? Oh, and notice that when I was counting bytes and counting lines, well, when I was counting lines, I was stepping through, but see, I was using a slightly different method. Notice that there's no index in here. This is the one that steps you through memory 1 byte at a time sequentially without having to pass an index. And it might be that these indices are the problem, because when I do it this way, this is just sequential access. This doesn't let you ever go back. This only lets you move forward 1 byte at a time. So it keeps an internal index, and you just keep stepping through the file 1 byte at a time. That seems to be really fast. But when I try to do it this way, it doesn't work so well. Okay.
One option might be to use the wrap method. It looks like it will just dump all of its data to the array that you give it.
Yeah, but there's no map for characters. Yeah, I looked into that. I've been reading this stuff. The trouble with that seemed to me like what would be the right answer, but there is no wrapper
Mm-hmm.
for Well, there's a wrapper for characters, but they're Unicode characters. These are ASCII characters. So the wrapper for characters is 2 bytes big. So then I would have to try to figure out how to unpack ASCII characters from inside the Unicode characters. That's not what I want. Otherwise, I'd have to wrap it. The other wrappers are as doubles, ints, and floats.
Well, I mean, you would just have to translate your A, R, D, V, A, R, K
Yeah,
into the numerical
right.
representations,
I
and
thought
it'll
about
work
that.
just fine.
Yeah. Well, yeah, it comes unreadable. Yeah, I was gonna try that. I haven't had time to try. That was a possible experiment because I saw that I could use a wrapper for ints. I could translate AARD into an int, and then search for that int. Yeah. So
That's what I
is,
did in my code, because a lot of stuff won't give me character arrays.
Yeah.
It'll give me byte arrays. So
Yeah.
I'll just cast my search string into an array of bytes, which the string class gives you a nice function to do.
Yeah. And that might be one of the things I could try. See, aardvark happens to be 8 bytes, so it's 2 ints. So I could search for aardvark by searching for 2 ints in a row. And I might, and I haven't had time to write. I had that idea. I thought that might work, and it'd be interesting to. But see, then the real question is, does Java's wrap method help or not? So, but that it just matters. Yeah, that's using these.
It's an inherited method in that class.
I thought it's in the original byte buffer. Yeah, I'm sorry.
Mm-hmm. Yeah, you give it an array, and it will just dump all of its data into that array.
No, I can't forget where it is.
Bottom.
The bottom. No, not that wrap. No, that's not the right thing. No, that's wrong. That won't work. I was thinking of another one. It's not that one. You definitely do not want to wrap these things. I'm trying to remember what the other one is.
Well, then it would be at the top, array.
View. No, it's view. What they call a view. Create a view. This is the thing that lets you see your memory as ints and doubles and things like that. Okay, they call that a view. So you don't map it, you create a view of it. Okay, so and they say up here that could speed up your code. Okay, so see, access to binary data. They talk about creating a view of your buffer as a potential way to speed things up. So, but you're still calling a get. You're still calling. Well, no. Where are those views? I forgot where I just lost them now.
So you'd want a char buffer.
Yeah, no, I don't want a char buffer because that's a Unicode char, not an ASCII char. But notice that they don't return arrays. They don't return arrays. Java for some reason is making this hard. Even these guys, even though they're creating views, they do not create a view as an array. They create the view as still another buffer, as one of these byte buffers. So it may be faster, it may not be faster. It would only find out by trying it, okay? All right, so let me show you some, okay. So these are interesting questions. This is real, this is real interesting way to think about programming, to think of true performance, of constantly asking yourself, how can I get the most performance out of the code I'm writing? Okay, now let me look at some other stuff that I was doing with this. I combined everything into one file. Let me show you. I'll put this all up on the internet probably later this evening, because I've been writing it a lot. So I haven't put the final versions of this up yet, but because I've been making so many changes. This one here does everything. It uses a fork join pool to create tasks that memory map files and step through the file as a memory buffer. Okay, so it's combining fork join pool and memory mapping. Okay, now here's the version of the file that does the fork join pool without the memory mapping. That's a pretty fast program. Okay.
Oh wow.
Okay. Yeah.
It's almost like 3 times faster.
Yeah.
Better than 3 times
No,
faster.
but this was reading the individual files, not the one big huge file. This was reading the individual files, which seems to. I'm actually surprised by this. It seems to be faster to read 1,000 individual files than it is to read one big file. And if you ever have copied 1,000 files from one drive to another, you know how ridiculously slow that is. And I thought that was a feature of the file system. And now I'm finding out it's not a feature of the file system. It's whoever wrote the copying program. Because this program is reading 1,000 individual files faster than it reads one big file. When you copy from hard drive to hard drive, one of the things you learn real fast is if you copy one huge file from here to here, it's fast. If you copy 1,000,000 small files from here to here, it'll take all day, even if it's the same amount of data. So I thought that was a feature of the file system. Now I know it's not. Yeah.
No, it's a feature of Windows. I've heard people in video editing having issues of stuff like that.
Yeah, Windows seems to be terrible at copying lots of small files. Well, Linux is not, it's better, but it also, I think, has that same problem. I think it's also slower on the equivalent. Suppose it's 10 gigabytes of data. If you copy a 10 gigabyte file from here to here, it's pretty fast. If you file 1,000,000 files that add up to 10 gigabytes from here to here, it could take all day, even though it's the same amount of data. Okay.
I can back that up because I've done stuff like that. It's better than Windows, but it still ain't great.
But here we see that I can now, in this case, I'm processing 2 gigabytes of file, over 2 gigabytes of data in 1,000 files faster than if I processed one file. Okay, all right.
It might be down to the way that Java handles when, like, I ran into this when I was doing image processing, multi-threaded image processing. If you have multiple threads trying to access the same object for data, Java, even if the object can handle that and there's no conflicts of reads and writes, Java really doesn't like it when you do that. It slows down a good deal.
Well, that's not what's happening here, because this is 10,000. This is 1,000 files. In the other case, it's one big file.
What I'm saying is, on the big file, you might have a bunch of threads accessing that same char buffer.
No, I think I know why. No, it's because I wrote this thing using the fork join. Remember, no, we can analyze it much better. When I have one big file, I cannot parallelize the I/O because there's only one stream. Yeah, you can't have two threads reading from one stream. When I read 1,000 files, I can have each file being read by a different core. So I'm getting that's what the fork join pool is doing for me. It's letting me parallelize the I/O. That's why I'm getting a speed up here, which seems to be what they're not doing when they do the file copying. Probably the file copying is not multi-threaded, and that might be why they have a problem. I bet the file copying isn't multi-threaded, but who knows? But that's why I think this is faster, is because it is allowing itself to parallelize the I/O across multiple cores, because every open file is a different stream. Okay. Now, when I memory map this guy, it's about the same speed. You know, turned out this time it was just a bit slower. I don't get any benefit from memory mapping it, even though, I should. Memory mapping is always referred to as the fastest way to access the data in a file. But again, I think I'm just suffering. I think it's these gets. I'm afraid it's these gets that are slowing it down. The only way to know for sure would be rewrite this thing in C++. And I would think that this version should be faster than this version, because this version uses the real file system. This version does all its I/O through the file system. This version does all its I/O through the virtual memory system by memory mapping. It should be faster. Okay, but this is one. In a sense, this accumulates a lot of what we've been learning in this class because it uses a little bit of everything. It's using a fork join pool. It's using two kinds of tasks: one task for I/O, one task for calculation. So I'm separating I/O steps from compute steps. These compute steps do the actual searching of one buffer. Okay? These I/O steps are the things that branch off the compute steps. So what this thing does is it takes the file and breaks it up into a bunch of buffers. It breaks the file up into a sequence of buffers. The idea being that you can interleave I/O with computation better here. By having a sequence of smaller buffers, one thread could be doing an I/O and being blocked on I/O while another thread is processing a buffer. One thing to play around with a lot is the size of the buffers. Up here is a constant. Where is it? Oh, here's the constant that determines the size of the buffers. Let me give this program a bigger buffer size. Let's see if it likes a bigger buffer size. Here's a much bigger buffer size. Let's see if that has any influence on the performance of the program, because that was a fairly small buffer. So it's hard to say whether a big or a small buffer will be better. A small buffer gives you lots of smaller jobs. A big buffer will give you fewer jobs, but a big buffer needs to do page faulting, because a big buffer would be multiple pages. So then your compute job is actually now doing some I/O, because this compute job would have to page fault more pages in. So it's not clear whether it's better or worse to make the buffers big. So here, just make the buffers real big. Well, that time it ran super fast. Yeah, I don't know if that'll, yeah. Let me go back to the smaller buffer. It looks like the bigger buffer is better.
Twice as fast.
Yeah, well, I mean, now you have, again, there's all kinds of issues. You have to run it a bunch of times because any given run could have been interfering with Zoom. With the, Zoom is doing its own I/O at this point. So my I/O system is being pretty much stressed also by Zoom itself. If you go here, Zoom's not really doing that much I/O.
Zoom is doing I/O on your Wi-Fi chipset, and
Well, no, it's recording everything to my hard drive.
Oh.
Yeah. It's doing a lot on the Wi-Fi, sure, because it's streaming your video in and streaming my video out. But it's also doing the recording to the hard drive.
Well, also your hard drive and your Wi-Fi chipset share the same bus.
Probably.
They both function over PCI Express if you're using an NVMe SSD.
Yeah.
And judging by how fast you chew through these files, I'm assuming you do.
Yeah. So, but that can influence your, any one run of these programs could have been affected by Zoom stepping in. So, we'll see. This is the small buffer size again. Okay. So this is the small buffer again. Run it again. Okay, 3, then go back up to the larger buffer size. Okay. There's the fairly large buffer size. And it does seem to like the larger buffer. Okay, yeah. Trying to find a good logical explanation for that could be challenging. In the real world of doing performance programming, it's a combination of analysis and guessing. Yeah, if it works, good. If it doesn't work, you might want to find out why, but if it works, sometimes you're just happy that it does. Now let's see, if big is good, how much better is bigger? Okay, there's doubling the buffer size one more time. Didn't change things. Okay, let me double it again. Okay, didn't change things. So I probably hit some kind of ceiling. You know, I'm making the buffer monstrously big now, and it's not making any effect. So it seemed to be, well, let's see, what was it? The one that seemed to be good was what?
256.
Yeah, let me have that. I wouldn't be surprised if the optimal buffer is somewhere. Okay, see, I bet that's not still the optimal buffer size. Let me have it again.
Yeah, still 1.7.
Yeah, see, well, it changed a tiny bit. Let me have it again.
Oh.
Still pretty good. Yeah. So, you know, the optimal buffer. Now, at this point, it's also the cache system. I may have just, since I'm memory mapping the file, and the file is going through the virtual memory system, the virtual memory system might be sitting there going, I remember these sectors. I've got them in my cache. So it very well might be at this point that we're seeing cache effects from the virtual memory system. Okay, so is it our code, or is it the cache system in the virtual memory system that's benefiting us now? You kind of find that out by rebooting the computer. I don't know if there's a way.
Disk IO has its own set of caches
And the
that
virtual memory
interact.
system, yeah, and the virtual memory system has its own set of caching. Now, I don't know if there probably is something that'll purge all the system caches. I bet there is a command somewhere in Windows to tell it to purge all the caches so you can get maybe a fresh run.
Hold on, your Windows has its own caches,
Yeah,
but also your drives have their own physical caches too.
Yes. But they're not that big. They're only 8 megabytes.
No, that's not true anymore. Like
how big are they now?
Your common commodity, like 1 terabyte hard drives, will have like a 256 megabyte cache, which is
no, that'd be 1/4 of the disk.
256 megabytes?
Oh, 256 megabytes. Yeah, well, that's a quarter of a terabyte drive. Yeah, so that's a quarter of a gigabyte. Yeah, so a quarter gigabyte cache on a terabyte drive.
And that does make a difference for most performance situations.
So
maybe not this one here, but most other ones it does.
Yeah, so we might even be getting performance boosts from the cache on the hard drive. Yeah, as opposed to it being our code, it could be a combination of the hard drive cache. Now, you know, if you're really trying to do this in the real world, you might want to find out, there ought to be commands to do things like purge the hard drive cache so that you can just start from afresh without having to reboot your computer. It'd be nice, it'd be nice if there's a way to purge the hard drive cache, purge the Windows cache, and run your program and find out if it's really your program that's running fast or not, or if your program's just cruising through the cache and getting most of its data from the cache system. Okay. All right. So the key of this was, for me, was that it isn't just enough to write parallel programs. I mean, here was it's not that hard to learn how to use fork join. What starts becoming harder is like trying to use it in a way that actually benefits you. Not just saying I know how to use fork join, but saying I could use it in a way that actually speeds things up. That's so much harder than just using it. It's so much harder to actually use it well than it is just to write the code that uses it. So I wanted all these examples for you to see that right. First of all, These parallel versions aren't all of them all that much faster than the sequential version. The parallel versions are sometimes a little bit faster, sometimes not faster than the sequential. There's a lot going on. There's a lot of uncertainty, that makes this stuff pretty tricky to analyze. Okay, let me see if, and then again, have good benchmarks. If you're really interested in this stuff, I decided to use Grep as a benchmark. That was an interesting idea. Awk turned out to be way slower than my own code, but Grep turned out to be just as fast or faster than my code, so that gave me a sense of something to strive for. Okay, Awk was as slow as the slow versions of my programs. So Awk, it's probably not optimized very much, or it's just or maybe it's just not a good program for searching. Grep is famous for doing searching. So I believe Grep has a reputation of being a pretty fast program. Okay, but again, well, actually, I don't know if anybody. Let's see. Let's Google multi-threaded Grep. See if any.
Someone's had to have done it. It's old enough where someone's tried.
Yeah, as just a programming, a senior design project. It's the kind of thing that somebody somewhere. Is there a multi? But it should. These are questions. If there's someone who's written one, it should just get it. We should be able to.
Multi-threaded Grep, GitHub.
Where? I'm not seeing it. Am I missing?
Patrick Zhao, you moused over it. Patrick Zhao, parallel Grep.
Oh, this one?
Yes.
Well, okay, so somebody thinks, okay.
The parallel Grep is a demo of how to apply parallel algorithm into Grep under the Linux system.
Yeah, I wouldn't be surprised if this was some sort of project, Probably somebody's project, because it would make a good project, write parallel Grep, okay? Not every algorithm lends itself to parallelization. So the underlying Grep, the underlying algorithm is regular expressions. And I have no idea if it's easy or hard to parallelize regular expression processing.
I looked into it seriously for about a day, and came to the conclusion that it would be absurdly difficult.
Yeah,
it would be doable.
Yeah,
but not something I want to do.
Some algorithms are famously hard to parallelize. This is one of the if we were doing a real theory course in parallel programming, one of the things that's interesting is that there are certain algorithms are famously difficult to parallelize. Some are easier to parallelize than others. For all I know, Grep might not be an easily parallelizable algorithm because it's implementing regular expression processing. So, it may not lend itself to that.
It depends on how deeply you want to be able to parallelize.
No, it depends on the
search.
algorithm. No, some algorithms don't lend themselves to parallelizing.
Oh, I'm just talking about regular expressions specifically.
Oh, I have no idea. I have no idea
if you
how
want
hard
to be able to parallelize a single matching process of one single expression, it would be absolutely insane and probably not doable with modern architectures.
They probably just carve the data file into chunks and just do Grep on each chunk.
Yep.
Which is more or less what we're doing. That's essentially what we're doing. We're just carving the data into chunks and doing our search on each chunk. Okay, and that probably would. Then you have to worry about the overlaps. Remember, I used to worry about overlaps. So any aardvark that happens to straddle two of my buffers is going to get lost because I'm not checking for aardvarks across a buffer. And I noticed that when I was reading about this, people overlap their buffers for that reason. So if I was to do this really well, instead of having one buffer start where another buffer ends, I should have a little bit of overlap between my buffers so that I could find an aardvark that straddled. So then anything that straddled the buffer would be in one, or if the two buffers overlap a little bit, then there won't be anything that doesn't sit inside of one of the buffers. So I'd have to overlap the buffers by 8 bytes. Okay, but that just makes the code a little bit messier to write. And in our case, there aren't any aardvarks to straddle the buffers because there's only 21 aardvarks and 2.3 gigabytes of data. So that's not a big deal. But so you'd have to account for you chop the data up into chunks, but then you have to count for what happens at the boundaries of the chunks. Okay, so I think that's all I had. Those are all the examples I had. The last one is everything we've talked about is in this one file here. This is parallel search with memory mapping. Everything is in there. This would be the one that, if there was going to be a fast one, it would be this one. And it was fast if we gave it, with the right buffer size, it probably was the fastest one of all these. Let's see actually about this one. Let me try one more thing. This is the one that doesn't do memory mapping, but I didn't try it with a larger buffer size. So let's just try one. So this guy runs. Well, see now this one's. I think the cache is fast. This one's running faster than it did a little while ago. I think
this is almost as fast as just counting bytes.
Yeah,
counting lines.
I think we've now got this file well cached into the file system, so that we're cruising through the cache of the file.
Well, keep in mind that even an SSD has a cache, and that cache can be a couple gigabytes.
Yeah. So I think at this point, anything we do in our code's not going to really change anything, because I think one thing you could do to flush the cache is just go read some big files and try to force them through the cache, and but that doesn't always work either. You may have to read massive amounts of data, because the cache system can be kind of clever about these things. It might not be caching what you push through the file system. If it doesn't think you're going to reuse it, it may not cache it. So you have to trick the file system into thinking you're going to reuse stuff. Mm-hmm.
Is your screen fully open? Is there 19,000 steals, or is there another digit? Like,
what? Say again?
For the steals, is there another digit, or nope? 19,000. Okay, thank you.
What, were you getting a different number?
Oh no, I just wanted to see if there was another digit there or not.
Yeah, 19,000 steals. That's not that many, because we're processing 50 million. I don't know how many. I don't know how many buffers we're processing, because the fork join pool is taking that file and chopping it up into buffers. So the number of buffers, I don't have a count of how many buffers there were. I
thought you chopped it up by line.
That was a different version. See, there's a whole bunch of different versions. Yeah, some versions chopped it up by lines. Some versions chopped it up by. Then what was the advantage? Chopping up by lines means I don't lose any aardvarks, because every aardvark has to be on a line. So chopping it up by line, guaranteed I never lost an aardvark. Chopping it up by buffers, I thought would be a little bit faster, but at the cost of, unless I overlap the buffers, of losing aardvarks.
So you said you wouldn't miss any buffers by doing by line, but something I've learned about parallel computing and processing this data set in particular, sometimes people typeset their book documents. So you could have an word split between two lines divided by a hyphen.
Yeah, if you're really if you're trying to do honest to goodness, real searching, you got to worry about hyphenated version. Yeah.
There are so many edge cases that I went through processing this data set. I could tear all my hair out.
Yeah, and in the real world, that's why you keep getting experts giving you different answers for the same question, because sometimes you forget these little edge cases. Yeah. So yeah. Oh, that's a good one. What if a word happened to have been hyphenated and a line break, and if you wrote a really, 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 really good search program, it should account for that. That just shows you how hard it is to write anything well.
The way that you would handle that in this particular instance is you would take your book, you would edit the contents by stripping out character terms and new line feeds into one line.
Right. Instead of trying to make your algorithm more sophisticated, you'd be better off processing your data to fit your algorithm. Don't fit your algorithm to the data, fit the data to your algorithm.
That's what I did to process this set.
That's probably the better strategy, is to clean your data and get it to fit your algorithm, rather than to try to write your algorithm for every possible version of the data.
Every single one of those edge cases that you code into your program is going to cost performance.
Yeah. The edge cases will slow you down, and then you might misprogram the edge cases anyway.
Mm-hmm.
Yeah. So you'd be better off pre-processing the data to get it into a very uniform form that you can then run a uniform algorithm on. And that's the kind of ideas that I think that's worth bringing up in this class. That's, if many of you could end up spending your lives doing this stuff because big data is becoming a big deal. So
Mm-hmm.
that's where a lot of the jobs are. So these are all issues that are real interesting to keep in mind if you're going to actually start processing big data. Now you're probably not going to write your own memory mapped versions of programs. If you do really spend your time processing big data, it'll be using things like MapReduce, Spark, Hadoop. You'll probably use libraries, but it's good to know something about how these libraries are written. So here we're looking at real low level, here we're looking at real low level stuff that would be part of a library. Memory mapping, fork join pools, trying to use low level things to implement our search algorithm. Okay. I don't think I think that's all the things I had to show you, all the different ideas I was able to come up with. Yeah, if there was a little bit more time left, the next step was to go up to all 40,000 files and all yeah, because see, these things are already running in under a couple seconds, so we could definitely, I haven't had time to, but all this code could probably just be moved to the big folder. I don't even know if I have it on my hard drive. No, I don't have all the data anymore. I deleted it the other day, but I think the code is really ready to to try processing all the data, all 40,000 files, but they have to be clean. Again, there could be bumps in the way because some of those files have binary data in them. It took me a while to clean up these 1,000 files. For these programs to work properly, all that data needs to be cleaned up because if there's any binary data in those files, it'll mess up these algorithms. Okay, but let's see. Okay, all right. Yeah, those are all. I'll put this code up. I'm gonna organize it a little bit better, but it's in a bunch of I forget how many. I've written like 50 or 60 programs already. Think of it as a progression of ideas. It's like reading a book. I tried to lay it out as a progression of ideas from simplest to most complicated, so you could see how you move through ideas of just reading files sequentially, reading files in parallel, reading files with different I/O systems, trying to speed things up and not if something turns out to be slowing you down, just don't use it anymore and stick with things that actually give you performance improvements. Remember the other day I pointed out to you that like scanner is horrible. Even though scanner turns out to be like what you see people use all the time, scanner from the point of view of performance is terrible. And some other things that you see all the time in books turned out to be not much better. So you have to find the things that work and then work with those. Okay. Now I gave you a little homework assignment. If anybody's got questions about the if you have questions about the homework assignment, yes, let me know. I'm perfectly willing to talk about these problems if you have questions about them. And as I said the other day, if anybody thinks they have some reference that's useful to share, go ahead and share with people. If you think that there's something that would be worth reading, I think everything we covered is everything we've talked about. All the ideas in this. This is not a research project. I think everything in this exam is stuff that we've talked about in the course of the semester. But if you think there's any reference that would be useful, I think it's a good idea to share it. And if you have any questions at all, just send me an email or let me know what questions you have. Does anybody have any questions offhand right now? Does anybody have any questions?
Would there be any value in going over the code that I gave you that like this data set was originally processed by?
Well, the bash code, no. I mean, like I didn't. I looked at the bash code. I don't. Bash code is so odd.
Oh yeah.
Bash code, yeah, nobody's gonna. Well, I shouldn't say nobody, but Bash code is Bash code is meant to be quick and dirty. It's not usually meant to be production code, and you can't write algorithms in Bash. Like you can't memory map files using Bash code.
Well, I mean, the bash code that I gave you was just glue.
Yeah,
That was just glue for a whole bunch of different methods around my processors.
uh-huh. But what were those processors written in? Was that the
R.
R? Okay, yeah, and I don't know R. Yeah, I looked at that code. I can't read R. Yeah, so I don't know. I don't.
R is very compact for what it does.
But the other issue about something like R is it's its own large system. You're not programming the computer. You're programming the R interpreter. It's a little bit like using Java. You've got a whole layer of stuff between you and the computer.
Oh yeah.
It's just, yeah, way worse than Java even. It's bad enough with Java. The Java virtual machine is complex enough to be sitting between your code and the CPU. R is going to be even worse. Yeah.
That entire project was written with the intent of being able to get a product that would do the processing before the end of the semester.
Yeah, so it may not be anywhere close to being as fast as possible.
Oh God, no.
Yeah,
no, not even close.
Right. So the goal here, what would be more interesting here is what would be real interesting here is to translate this Java code into C++, because that would be the real benchmark of, you wouldn't want to translate it into C. C's too low level. C's not going to give us access to, thread, like there's no thread pool that you can access easily in C. But C++ has fork join thread pools built into it now, just like Java does. So C++ gives us a sophisticated library like Java does that we can program with, but that library is closer to the CPU. So there's not this JIT compiler laying around that just can cause us all kinds of confusion. So it would be another good language to write this in would be Rust. Okay, it would be very good to rewrite this stuff in C++ and in Rust. That would be a real good project. All these examples, and it wouldn't take that long because once this code is written in one language, it's usually just a matter of translation. You're not starting from scratch. I don't think it would probably, I bet if I translated this into C++, it would take me a couple weeks. Maybe take me a week or two to translate this into C++. And Rust would take longer. Okay, but it would be then you'd have something to really compare, then you'd have some way of really benchmarking. Then another thing to compare this to would be to use a real big data library, like Spark, which I'm not that familiar with, but those are the libraries that are really meant to process gigabytes of data at a time. So it would be interesting to see, then you wouldn't be writing code like this. You'd have to write the code to be specifically for the Spark library. It'd be a little bit like using R, but Spark's meant for big process. R is a statistics library. Spark is big data processing library. So you'd have to write.
The main goal of the project was to do statistics on the data set.
Now, Spark will do that for you. Spark is a statistics tool, but it's specifically meant to be a tool for processing big data and getting statistics on big data, as opposed to R being just a statistics tool. R really is a tool for really computing statistics, as opposed to Spark is really a tool for processing big data, which has statistics tools built into it.
The only thing that R does fast is piping data around between function calls. It does that lightning fast. Everything else is slow as molasses.
Yeah, and that's part of Spark. Part of Spark is like we haven't done pipelining in here because there's been no second step. The results we get, we're doing just one step at a time. Like we've been searching the file for the words aardvark, but we haven't been doing anything with those results. That would be like a pipeline. If we were to do something if we were to process the data, and then, like if we process 2 gigabytes of data and got it down to 1 gigabyte of data, then there might be another step on that 1 gigabyte of data to process it down to half a gigabyte of data. There might be steps, but we don't, like here we're just concentrating on one step, so we don't have a pipeline. but that's an important part of things like Spark. Yeah, they put a big emphasis on pipelining the data so that you can do multiple steps. Here we're looking at the code for one step. The code, like, just take that massive piece of data there and just do one step on it. In our case, search for aardvarks. Okay. Okay. So I think we'll just stop there. If no one has any other question, we can just end there. Like I said, I'll try to get this code up in the next day or two, and I hope, I hope it might be useful for you, that if you're curious to see, like, especially for if it's Java, what are the different techniques for trying to process a large amount of code in data, process a bunch of code in Java. This gives you a little bit of a sense of how you might do it. Okay. All right. Again, if you have questions about the last homework assignment, let me know. And I'll go ahead and, okay, say good night. Bye-bye.
You guys.
Good
Good night.
night.